All right, let's go ahead and get started. So welcome to Chem 221. So hopefully y'all are in the correct place. My name's Marissa Shepard, so I'll be your instructor. So I'll put my email on the board. And I'll also write it in our notes here. So Shepard. So email is the best form of communication. So at, oops, I misspelled. So at roguecc.edu. And so I'm happy to be here, happy to be your instructor. So I'll tell you just a tiny bit about myself. So I'm really bad, by the way, about talking about myself personally. I'm always an open book, so you can always ask me questions. But, you know, I'm here really because I love teaching. I love teaching chemistry, and I love teaching y'all. So some of you may know me, but I was pregnant last year, whatever. I had my baby. That's wonderful. And I decided not to take full time off, so you'll see I'm only teaching this class this quarter because I really wanted to be there for y'all, right? So I am here to teach my 200 level babies, right? Because you guys are my chem majors or science majors, right? So I know not everybody is a chem major, but obviously we're going to talk about the importance of chemistry. And so I want to make sure you guys have a really strong background, again, hence why I'm here to teach y'all. And so obviously I'm getting you through this course. We're going to take a nice deep dive into Gen Chem. But my goal is also to get you to the next step, right? So hopefully we have probably like some pre-meds in here. You know, maybe you're going to go to grad school one day. So again, we really want to dig down, right? Like actually how to think like a scientist, how to think like a chemist, right? You know, again, I'm not here to teach you what to think. I'm here to teach you, right, how to think critically, and really, again, how to start kind of applying a chemistry mindset to everything. But before I get too excited, so again, just some housekeeping things. So everybody should be enrolled in Chem 221, so that is now the lecture portion. And then you should have signed up for 227, and so that's the lab either on Tuesday or on Thursday. And so hopefully you got my announcement, because lab does begin today. So if you sign up for the Tuesday section, we will have our first lab today. And so I try to send an announcement of wear cotton. We'll get into safety stuff why, but the lab is printed out there for you. All right, let's take attendance, like I said, before I'll get excited and carried away in a second. All right, so I don't normally take attendance. I'm just taking it the first day. And then if I butcher your name, just correct me. If you have a nickname or alternative name, you know, just let me know as well. All right, Charlene, I see you. Emma. A, okay, perfect. Bernardo. Nathan, I see you. Sydney Bowers. Sydney? Yes, no? Okay. Holden, or Todd, sorry.
Here, Holden.
Oh, Holden's the first name? Okay, sorry. Eric. Alexander.
Right here.
Happy. Ethan with a C. And you guys aren't Sydney, correct? Nobody's Sydney? Okay, we're still going through the roll. Sorry, you came in just the middle. Dyson. Yeah, there's seats up here. It's going to be a full house. Dyson. Any Dyson today? Going once, going twice. Okay, Finn. Felipe.
Here.
Derek.
Here.
Ellen. Lucian. Tyga, sorry. Gabriel. Annabelle. Ariana. Do you want me to call you Ari? Katharina? Cat. Okay, perfect. Sorry, let me write that. Raviel. Tanaya. Leanne.
Here.
Jacob.
Here.
Malathi.
Malathi.
Sorry. Skylar. Kyler. Oliver. No, Oliver James. Okay, going once, going twice. Max. Matthew.
Here.
Brooke. I saw walk in. Oh, there you are. Matthew with an M. So Matthew McVeigh. No? Okay. Francisco. Alana. Elena, sorry. Johanna. Did I say it right? Joanna? Okay. Hector.
Here.
Peter. Peter R. Okay, no, Peter. Diego. Cohen. Come on, roster. Go, go, go. Okay. Damien with an S. Ian. River. Alexis. Olivia. Max with a T. Max Terse. Going once, going twice. Okay, Gavin.
Here.
Perfect. All right. And how are we missing people? All right, excellent. So thanks again for being here on time. Let's do a little bit of syllabus stuff. And so I have my course shell. And so I apologize. Somebody already sent me a message that the dates are wrong. The dates are going to be wrong. And yeah, I'm not the biggest fan of Blackboard. But I'm going to make a disclaimer now. So Blackboard is not an accurate representation of your grades. So Blackboard is not. So we'll talk about what your grades are made out of. And so yeah, Blackboard has a mind of its own, especially when it likes to publish like what your total grade is. It's like everybody's either getting an A or an F and it's wrong. So just ignore Blackboard for the most part. And yeah, you're graded on a curve anyways, which we'll talk about again as we progress. So looking at the syllabus, so your syllabus tells you how everything is weighted. And so most things I'm going to hand to you. The only thing that might sneak up on people and has historically snuck up on people are these reading questions. Oh, what's your name so I can get attendance?
Matthew McVeigh.
Matthew McVeigh, perfect, thank you. And so these reading questions, so I have, and I'm trying to rebuild my shell cleanly. That never seems to happen. So week one, there they are, reading questions. So they're there, and so you have 2 this week to kind of keep up with the reading. And so this is the only thing found in Blackboard for your assignments. And so there is homework there posted, right? So I post the homework, I post the labs, but I'm going to hand you everything you need, right? And so that's how the class is going to work. You can walk in on Tuesday. I'll have your homework handouts, your lab handouts. I'm not going to, if you look at the lab, so this is kind of jumping around. So the lab does ask for like pre-lab questions, but I'm not going to check them before the lab, just because I don't expect people to like have access to a printer. And then if you're the Tuesday lab, right, you're just walking in, getting this today. Well, you may not have time to do the pre-lab questions, but I do expect them to be done when you turn in the lab, right? So you don't have to have them done before, just after. Does that make sense? I just want to make sure we all know, again, where our grade is coming from. So again, I'll put that in here. So again, the only thing you need to do on your own time are those reading questions, and they are associated with the textbook, right? And it's just to help you kind of read the book and digest the material. And again, right, 200 level class, you are kind of expected to read and delve into this textbook. And those are easy points that you can earn on Blackboard. So you'll want those, otherwise you're losing out on those free points. Sorry, obviously I can't talk and spell. All right, let's go back to our syllabus. So, okay, those are the reading questions. Homework. So homework I don't grade for accuracy. You just turn it in. I'll kind of glance over it. You know, sometimes if I see something egregious, I may make some notes. But you're expected to kind of check your homework. And it should be posted there. Maybe I didn't. So I need to, oh, no, it's in here. Sorry, I'm blind. So homework answers are already posted, right? Check yourself. They're there to help you study. Obviously, it doesn't do you any good, right, to just copy the answers. You can do that all day, but you won't do well on your test. And so then quizzes. So quizzes are going to be done as part of recitation. So again, kind of the format is we have 2-hour blocks. So we'll do lecture from 11 to 1 today, right? Yeah, so we'll do 11 to 1. We'll take an hour, a 10-minute break after an hour. And then on Thursday, we'll kind of lecture for, again, an hour, and then we'll take our break. And we'll generally have a quiz. We may do some other kind of assignments as well to kind of practice. But that's kind of how the format of the class is. And so recitation, even though it's kind of a loose time, you want to take advantage of that, right? Ask questions, do your homework, you know, get anything done in that time frame, as well as the quizzes. And so, right, you will get a paper quiz on Thursday. You will take it then, and so don't miss it. And if you do miss it, right, you can make it up, but this can also start hurting people as well. And then we'll have exams, so we'll talk about that as we get closer. It's on the syllabus, so we have a midterm and a final. And then labs. So generally people do really well on the labs. Are kind of meant as a buffer. Again, just you go to lab, do the experiments. You're expected to go to lab and do it in person. So there's generally not room for, you know, like dry labbing. If you get sick or something, we can arrange a makeup day. And so blah, blah, blah. So we'll do all the labs. And then we'll talk about this. So at the end, we'll kind of do a small journal article review. And so that's to kind of get us looking towards the future. So if you take the whole series of this, the very end is going to result in a research paper and a small mini poster presentation. And so we just want to, again, start looking at the literature. Any questions about the format of the class? And then so other syllabus things. So goggles are actually provided. Goggles and gloves. And so we have, you know, the nice goggles that stick to your face. And then if you prefer something else, so you're more than welcome to purchase your own goggles or glasses. So I brought mine, and so if you are going to purchase your own glasses, you have to ensure that they have these safety side shields here, right? So they kind of protect your face there on the side. So again, you're more than welcome to buy your own, and I understand, right? Especially if you don't like having your eyeballs suffocated. And so purchase one now, especially again if you're going to be here all 3 quarters. And what else? So I guess we should talk about the textbook briefly. Did y'all see this online? Was this in the bookstore? Did that get posted? Okay, good. Because there's some issues with that. So I really love this book. And I pick it over and over. And I mean, it's an excellent book. It's very detailed. It's written to a great depth. The math is excellent on it, right? Uses textbook. It just doesn't get pushed often because Macquarie has now passed away. So the copyright of this book, I think, is like 2010. But chemistry doesn't change. And again, that's why it's not going to get pushed to the forefront by publishers because, right, new people want to make money, and obviously they're trying to get their textbooks, which I think are frankly inferior to this one. All right, let's see. And then the other thing I want to emphasize, right, well, chemistry is hard, and, right, I want you to succeed. Right, so ask me questions early and often. Again, I'm here to help you. So generally, so I'll just say, right, office hours are kind of in general before or after class. But I would really, again, just email me for an appointment. You guys are the ones with busy schedules, right? Half of you are running out of class to go to a job or something. So just make an appointment with me, right? Email me. You can also send me screenshots of your work, right? You're working at home, 11 o'clock at night, midnight, whatever, right? Just send me a screenshot. You never know when I might check my email too, right? So just email me early and often for help. And then I need to post it because Kevin Colhane is doing tutoring as well over Zoom. And then I'm not sure what the situation in the tutoring center is, who's tutoring. Okay, because I was going to ask if Ben Franklin is around, which sounds funny.
Yes, he is.
But yeah, there's this guy. I've actually never met him, but his name is Ben Franklin, and he's apparently an excellent tutor. So yeah, if you hunt him down in the in-person tutoring center, I think that will work out. But again, also come to me. Like it may not happen so much first quarter, but I know sometimes like third quarter, second quarter, the tutoring center and Kevin kind of get lost in the math that we'll tackle. And, you know, the math in here isn't too difficult. It's just kind of sticky algebra. All right, any questions, comments so far? Have I covered everything? We're all in the right class? All right, and so that's another thing, right? Ask me questions. I'm happy to answer your questions. And then if you ever want a more like in-depth topic, and we'll kind of, we'll get to what I'm kind of referencing in a second. I'll say email me, right? Like just email me so we don't get too sidetracked in class. All right, so now, well, what is chemistry, right? Why are we here? And so I kind of want to hear from y'all. So I was kind of making guesses of what majors we have, but what majors do we have in here? What interests?
Environmental science.
So environmental science, excellent. So right, we got that in here. Do you know what you want to do in environmental science?
Consulting, probably. I'm not sure yet.
So some sort of, I mean, there's lots of consulting, right?
I know, it's very broad.
And then like with that, right, there's so much chemistry in environmental chemistry. So I feel like environmental science is just, right, applied chemistry. And so we'll get to a ton of that in here. What else do we have?
Pre-medical studies.
So pre-med, so right, we can go all over the place. Where's my medicine? There we go. So pre-med. So right, you want to understand everything from units, so you know how much, right, medicine to give a patient. You want to understand chemical reactions, how that works in the body. That can go into like drug metabolism too, and kind of drug development. What else do we have?
Nuclear engineering.
Nuclear engineering. Where's my nuclear? So I'll just put happy face. So right, obviously understanding nuclear reactions. We'll touch a little bit on that. We'll do a fun lab. I can't remember, it's second or third quarter about radioactivity. What else do we have?
Biology.
So biology, so it's pretty broad. What are you interested in? You like plants? You like?
I mean, conservation is more like environmental.
So kind of more environmental, put conservation. I mean, I'm also thinking, this makes me start thinking of like nitrogen and nitrogen fixators and like repairing the soil and getting into that. What else do we have in here? There's a lot of you. You gotta have a lot of majors. Unless y'all are all pre-meds or all. Don't be shy. Yeah.
Aerospace engineering.
Aerospace. What else?
I'm actually doing health and exercise science through SLU right now for physical therapy.
So health and exercise. Excellent. So let's talk about both of those. So right, aerospace, you have, again, units. You have calculating, right, how much fuel and how many chemicals you need to kind of provide enough lift to get off the ground. Or you could get into, like, the materials of it. So obviously, right, you have to have materials that can withstand extremely high temperatures and extremely cold temperatures potentially in space. So wide extremes. So all sorts of engineering going into that. And then, right, health, exercise, again, thinking of like metabolism, calories, joules, right, all that's related, how we convert chemical energy, right, or chemical potential energy of food becomes kinetic energy. What other interests do we have in here? Neuroscience. Put that over here. So again, right, kind of understanding those chemical reactions, or even, right, I don't know what part of like neuroscience you're into, because like you could go into the chemistry of it, which always turns into like drug the class, I like to joke. But, you know, that's relevant, how you design molecules to cross that blood-brain barrier. Or I don't know if you're more like materials focused, like trying to put nanochips into people's brains, but I don't know if you wanted to elaborate.
Oh, you're asking.
Yeah.
Okay, well, I'm just majoring in neuroscience. I'm going to transfer to U of O. I haven't really figured out which aspect of it I'm going to like focus in on, and kind of figured I'm going to get more into that once I actually transfer.
Yeah. And so that's a good thing to do in this class too, to kind of start thinking about, again, you know, we're going to do a journal review over some literature papers. And so you might want to start delving into the literature of topics that you like, right? That's what I'm trying to encourage, is you all have your own interests. You should look into the literature for that. And so with that, right, ask me if you ever run into a paper, because that's going to happen, right? And this is going to start me getting on a tangent potentially. But so if you run into a paywall, just email me for a journal article. So I still have ways of getting around these paywalls. So I have like old connections with my PhD university, so I still have that email, so I can get past the paywalls, and also an ACS membership. So right, so when you're looking at papers, you find something cool, just send me an email, and I'll try to get it for you. I can't get everything, because sometimes they're a little too expensive, again, depending on the journal, but I'll try to get what I can for y'all, because again, I want you guys delving into your topic, looking in the literature, right? That's what we should be doing at this level, or starting to get into. Yeah?
What did you do for your PhD?
So I made silenes and germalenes and bimetallic catalysts, so kind of using the first row transition metals to save the earth. So of course I was going to convert CO2 to ideally like methanol or something, some sort of fuel. I only ever made it to formate, or small molecule activation, like doing N2 to ammonia. But yeah, and I could, later we can like go down the rabbit hole. You could look at my thesis, like you can Google me pretty easily. You have to use my maiden name. Anyways, and so right, we're kind of getting into this, and obviously I'm biased. I'm a chemist by training. But I see chemistry as kind of, again, our central science, right? It builds a lot of fundamentals for all these things that we're interested in, right? Medicine to the environment, aerospace, any sort of engineering, right? We have to understand chemistry fundamentally. And then, right, just understanding what that is. And so, of course, chemistry is just considered the study of matter, and well, matter is anything and everything that takes up space, right? So obviously from our gas to any material, obviously I'll talk a lot about drug development in here. And so, right, we'll be looking at these different things. So we have chemical changes, which we'll be looking at, where substances are used up and transformed, right? So they'll go from one arrangement to a new arrangement. So rearrangement of atoms. And so of course, right, we can see a nice example of combustion there. So propane burns in air, and then, right, that is converted to carbon dioxide and water. So just kind of, again, giving you a sense of what we're doing in this class. And then, of course, we'll look at physical changes. So a physical change, right, matter does not lose its identity. And so it just changes either states of matter, or, right, it could be crushed or physically altered. So crushed, torn, and then I'll add dissolved to this. This is one that tends to trick people, right? So think about it. Okay, you put sugar into water, stir it around. So, right, it didn't do anything. It didn't react, right? It's still sugar. It's still water. And you could, of course, separate it back out, which is, again, also what we want to talk about, chemistries. So I had an advisor that once said, my 3-year-old can mix chemicals together, right? It's what makes a scientist is being able to, right, purify and tease your products out. And what's your name? Sorry for roll.
Max Church.
Perfect. All right, thank you. And so again, right, physical changes, and I'm sure everybody has seen at least water in all 3 states of matter. So of course we have solid, ice, and then you add energy to that, and then it becomes liquid, of course, and then you may even take that, right, and boil it to become gas. So, right, we've seen that. So again, that's an example of a physical change. All right, so let's look at, so now this is starting to get into, right, like how is research done and how is science done? And we have, right, the scientific method here. And so this is, again, kind of an oversimplified view. So it says, right, usually we start with some sort of observation and curiosity. And so let's define some of these terms. So what's a hypothesis?
Just an idea that isn't really based on much evidence, or
Here, Max.
It's an educated guess about something that can be tested.
So educated guess that can be tested. Good. And so, right, so again, that's kind of the key is the observation and curiosity, right? So you see something and then you think, okay, well, let me test this. So there's our forming our hypothesis, making a prediction. And so then, right, we perform an experiment, make some observations, and then either kind of, again, we're going to talk about why this is a very rosy picture of science. So, right, just saying, okay, we do this a couple of times, and then, right, eventually we publish. So, yay. And, right, we add to the body of knowledge. And so now let's look at these 2 different terms here. And so I don't think it's very clearly defined here because I would use different terms. So what's the difference between a law and a theory? And examples might be more helpful. You could also give an example of a theory or a law.
I guess.
Yeah.
Is it a law is accepted by the science community as kind of like a fact, more so than like a theory is?
Well, they're both kind of accepted, but there's a little key between the 2. Yeah.
Is like a law like proven beyond a doubt that it's like absolute, whereas like a theory is like even if you have a bunch of evidence, like you can't definitively
Yeah, I mean, you're so close. There's just like, so the law is more, and I'm looking for like a mathematical relationship. And so, yeah, you're correct in like it's an observation, right? People have seen it a million times, but it's also, again, usually, right, mathematical. Like, you know, we can drop this pen thousands and thousands of times, and it will always fall at the same rate, right, due to gravity. You have, right, E equals mc squared. And so, yeah, we can say that it's some sort of proven relationship. And then again, right, that's usually why I put the term mathematical, though. And I'm sorry I can't spell, so just, you can either correct my horrible spelling or ignore it. Again, I apologize. So I won't take off for spelling, that being said, so since I am a horrible speller. And so again, like F equals ma, you can do that hundreds and hundreds of times. So, right, force equals mass times acceleration. And so then what's a theory? And you kind of, I think you kind of said it where it was like proven, but we can't like definitively say it. So what are some examples of theories then?
Evolution.
So the theory of evolution, right? So again, it's a theory. People think they have evidence for it, right? Looking at fossils, but no one has been there, right? No one has stood there from the beginning of time and watched this happen. So we can only, again, surmise what happens. What are other theories?
Relativity.
So theory of relativity. So again, right, we can only do so many experiments to send your twin off into space, but what other theories do we have?
Electron field? I think that's a theory. I think I've seen the word theory after.
No, I'm not sure. You got me stumped on that one.
I was trying to read about it, I was like, I still don't understand.
I was thinking like Big Bang Theory, you know, same thing. Like we have evidence of an expanding universe, but no one was there to see the Big Bang. No one knows what actually happened. Germ theory is also a theory. So again, right, the idea that small organisms or something, right, invades our body and causes sickness. And, you know, again, I think we're working on our refinement more and more of viruses and bacteria. But all that, again, relates to kind of germ theory. And so, again, I think I like your definition. So we'll say, right, an observation or relationship that has been proven many times or has been proven, that's not really, I'll say shown, and lots of evidence around. Again, Big Bang, right, expanding universe theory, but no one was there. And so, yeah, ultimately, right, it can't be proven is the caveat, right? It can't be proven definitively. So again, right, no one stood there to see evolution. Big Bang theory, again, no one was there. But law is, again, our proven relationship. And so again, right, this kind of gives a very rosy picture. Oh, let's define these two terms. So what is qualitative data? So what kind of data is that if something is qualitative?
Non-numerical.
So non-numerical, that's a good definition. So, right, anything else, so kind of descriptive. So it could be any sort of taste, color, you know, explosions, whatever happened, right? You saw something. And so then what would quantitative be? You could use his definition. Yeah, numbers, right? Is that what you said? So numbers are numerical base. And so that could be amount. So we'll talk about any sort of, right, boiling point, melting point, length, width, height, dimensions, right, density, all sorts of things. So lots of things with that. All right, so let's look at some science things. And so I have these links pulled up. And so let's look at a few things. So historically, I've always shown this blog post and this kind of example. So now you can see it's kind of been a long time. Let's look at this article. And so this was an article that was actually posted, like published, right? And it was published in 2013. And so you can see that it was withdrawn, or maybe that was when it's updated, sorry. I think this was 2010, or I don't quite remember. Let's see. Doesn't have a date. And basically, like I said, the blog post has been taken down since it's so old. Basically, again, this got published, so let's talk about how papers are published, right? So you're a professor, you're trying to publish a paper, and so you're trying to select a journal, so you try to select whatever journal you want it to go to. They have different impact factors and blah, blah, blah. But then what's kind of weird and people don't realize is you pick people who you want to review your journal, right? You say, hey, these other professors are doing similar-ish research so they can understand it, so they're, send it to them so they can kind of read it. But then, right, that's the thing to remember, that these papers are not tested, right? So someone just kind of reads over it, but no one's going to go into the lab and reperform an experiment. That actually only happens with one journal, so that's Organic Synthesis, and it is known for that. And it is like the best journal for published preps because someone has checked it, so it's going to work. And I can't, not to go down the rabbit hole, but I can't tell you how many times a chemistry prep is what I would call not very descriptive, right? Because they don't want to tell you some little trick that was key, like, hey, you really needed to use ether or else the whole reaction explodes and does horrible things. But they might conveniently leave that out. Anyways, so this was published, and I don't know if you can tell. You see those images? They're more egregious down here. But they were certainly, this is a better zoom in. So can you tell what's wrong with that picture? Especially like this one. So does that?
Is it that they're pointing away from each other?
I mean, it's photoshopped. I don't know if you can see that, but let me see if I can zoom in any more on this picture. And so it's kind of hard to tell, right? They took their time. This one they were a little sloppier with, but it's literally photoshopped. So that was their whole publication, right? It was like, we can do this cool thing, electronic tuning, and they can make 90 degrees golden nanorod chopsticks, right? That was their whole paper. They literally photoshopped it, right? And then it got past reviewers, it got published. It was just that people were reading the paper, and somebody eventually noticed, hey, this looks photoshopped. And so it was retracted. So long story short, right, it was eventually retracted. So there's, science is self-correcting, but, kind of on what time scale. So this one was caught reasonably quickly, but I also think that it was pretty egregious that, it's kind of unbelievable it got published in the first place. But that's all to tell you, right? Scientists are just like any old people, right? So that's the other thing is like people get this rosy picture of scientists that they're like wonderful, benevolent people, right? But they're just like anybody else. So they want to get money, fame, right? Funding's always hard to get, so you might, be under pressure to publish questionable things so that you get funding. People lie. There's all sorts of things. So I'm just saying scientists are not innocent. So you have to have discernment. And so let's look at a few other things. This is just something that I wanted to share. So a lot of people are kind of like in panic about ChatGPT and AI and what that means. I'm not terribly panicked. People have been cheating from the dawn of ages, and AI just like helps you cheat faster. So if you want to cheat, there's more tools. That's all. That being said, ChatGPT is not the best with math. I've caught it making mistakes before. What it is okay for, I think, is like pulling references. So I don't know, it's like ChatGPT, find me papers about blah, blah, blah. And then, it'll give you papers, but just check them, right? It's very easy. Just go look them up on the direct website where they were published. And so I did want to bring out this caveat, since especially I didn't bring up this paper, but retractions have increased, right, since like 2020. So that's kind of an issue. Obviously, right, COVID, there are a lot of papers being published at that time, and that kind of probably led to a bunch of papers. What's your name? Sorry, so I can take your, sorry? Dyson. Perfect. So yeah, there's been a lot of retractions and so forth. And so kind of the problem is ChatGPT might ignore retraction. So that's why you don't want ChatGPT to just spit you out whatever conclusion, right? You want to go back, look up the papers themselves, make sure they check out, right? I've never had this happen, but I keep hearing where like ChatGPT like makes up sources and books and all sorts of things. And, so just check everything. That's all I'm saying. And so let's look at some other things too, because again, I really want to encourage you to look at the scientific literature, because the world that we're living, right, there's always sensationalized headlines, and even chemistry magazines are no different. So I was shocked for a lot of reasons. So I feel like I missed the boat on like social media wise, because like I don't know why everybody is saying that this doesn't have backing. So like I said, I was shocked that even my chemistry and engineering magazine claimed that Tylenol and autism has no relationship. But if you look up papers, you can actually find, right, people talking about this. So this has been known, right? But again, right, correlation does not equal causation. And so that's what I want to get to in this class, right? We need to have a high-level, nuanced discussion of things and think about, right, how this is reacting with our body. And so to kind of look at the paper, I think I posted it on Blackboard already, so you can look through it yourself. But basically, I wanted to show you this, right? Because again, we want to take it back to the chemistry. And so it's not saying that every time you take acetaminophen, right, that it's going to necessarily result in a birth defect. You don't know that. But we can look at the mechanisms by which acetaminophen is metabolized by the body, right? So going back to, you guys want to be doctors, right? This is medicine design, why it's so difficult even to design medicine. Because once it goes into your body, who knows what happens, right? And then trying to trace those metabolic products is not always easy, and then we get into labeling experiments. And so that's what it talks about, is, okay, we have acetaminophen, and it has these two different pathways for degradation, one involving sulfation, and then this other one, which it reacts with glutathione in this reaction here. And so here's another pathway. And so basically it's saying, and again, if you're pregnant, this tends to kind of put more strain on your amino acids. Obviously, right, you're trying to build a new life form. So it's saying that, yes, if you have lower glutathione levels in pregnancy, then that can result in a pathway that results in bad products, right? So then it's saying that now this can cause DNA damage and, right, affect the mitochondria. And so, right, all I want to tell you is, right, your body is a complicated chemical reaction, right? So there is a pathway. again, obviously, correlation doesn't equal causation, but there is a risk, right? And so that's, again, what we're kind of going at. Dosage makes the poison too, is the way we can kind of look at it, right? So again, we're just kind of looking at drugs and how they interact. And then again, take everything with a grain of salt, especially on, the social media and mainstream media, right? Everybody is always yelling in one direction or another, always crazy. But science usually isn't that polarized. So again, right, we see that, it's very reasonable. We can see these metabolic pathways exist. All right, so that being said, oh my gosh. So that being said, again, right, you want to look at the literature. So look at the literature yourself, right, kind of see where it's at. And again, right, scientists do not always have all the answers, right? It's easy to kind of propagate errors too, and you don't really know, right, until you're looking back 10, 20, 40, 50 years backwards. Like, that's just science. And again, everything is so highly politicized that it creates quite a sensationalized atmosphere. All right, let's take a small break before we shift in there. So yeah, we'll take a quick 10-minute break. So again, I probably stretch your legs a little bit. So let's meet back here at 11:56, and we'll start looking at our metric system. Did we all make it back from the bathroom okay? All right, so I knew I forgot to mention at least something. So on my Blackboard page as well, so if you ever miss lecture or want to rewatch a lecture, I have a link here to the YouTube stream. I'm not going to click it right now because then we'll start getting Inception vibes, and I don't want to do that, but it'll link to the class YouTube. You can look at all my old lectures there if you get really bored, but I mean, please don't. Otherwise, again, you can catch up on the lecture that you missed there. So yeah, or again, review. So that's a handy tool there. And then I also have useful resources. So if you don't have your textbook yet, I think the first 4 chapters there are posted for you. And we'll get to that later. Yeah, these are other helpful tips, but you don't need necessarily all that right now. So yeah, just the YouTube page, though, is useful. But like I said, you have to make up labs. All right, so back to our topic here. And so before I get too excited and start diving in, so again, we could be at different levels here, right? Like I've had some people that have taken my Chem 104 class in here, I think both in person and online. And so, right, you may have done this, or you could be a completely blank slate, never taken chemistry, right? That's okay, too. You know, you're just going to have, it's a lot to do, but, you know, it's again, totally feasible. And so I'm trying to, like, go fast because we have to do 2 chapters in 1 week, but at the same time, right, ask me questions if you need. And we will spend recitation time kind of working on this. Oops. So, right, so if you want more kind of hand holding with the conversion factors, that's what recitation time is good for. But again, like I said, ask questions. Otherwise, I'm going to try to keep it moving because I'm assuming that most people at least have some understanding of metric units. But let's look into this. And you should also be able to follow my notes online. They're like posted live, so you can see that. If they're not functioning, let me know. But let's just kind of ask ourselves this. So how do we deal with the small and the large, right? And so some people, right, if you're a biologist, you're going to be looking at human hair, or maybe you've taken our nice forensics course here. I think you look at some human hair in that class. But what scale is that? Anybody know? It's kind of fun trivia. So what did you say?
Micrometer.
Yeah, micrometer. So it's about the order of 1 micrometer. And then does anybody happen to know what power of 10 that is? What did you say, -6? Excellent. So 1 times 10 to the -6 meters. So good. So again, if you're completely lost, that's okay, right? Just try to take it in. And then what about the size of an atom? What scale are we working on? There's kind of 2 answers for this potentially. Angstrom. So excellent. So that's a special unit for chemistry. So I wasn't really expecting anyone to know this, but good trivia. And so it's this little A with a weird circle on there, and that's for 1 times 10 to the -10 meters. And again, I'll write that angstrom. But then if we're not using the special unit, what else might be close in size? So nanometers are 1 times 10 to the -9. And so you might see both of these units when people are talking about atoms or the size of atoms. And then what about an elephant? So now, and let's think about the mass of it. So what scale is that on now? Come on, biologists. What are some units?
Kilograms or tons?
Yeah, kilograms, tons, So, right, again, I'm not the greatest biologist. I'll say about 2 tons or, roughly 5,000 kilograms or so. Again, depends, right, what species, male, female, but roughly that. And then, so kind of last trivia, so if you guys like space, now you're dealing with extremely large units. So what's the unit that's typically used in space?
Light year?
Yeah, light years. Does anybody happen to know how far Alpha Centauri is in light years?
4?
Yeah, about 4. I have 4.35 on my notes. But yeah, about 4 light years. Oh, let me write that out. So light years. And so that's about, I think, 40 trillion kilometers. So I'll just write it out. So kilometers. So, right, extremely large. And so again, I think many of you are familiar with scientific notation already. And so it's used to represent, again, very large or very small numbers. So again, depending what we're talking about. And so just a quick reminder. So if it's negative, right, then we're making it smaller. So move the decimal 1, 2, 3, 4, 5. So right, 2 times 10 to the negative 5th there. And then for large numbers, so 1, 2, 3, 4, 5, 6, right? So 2 times 10 to the 6th. Again, I think everybody is okay with that. Not trying to move too fast. And again, please, please, please ask for help if you're lost, right? Like, I don't want any, like, one person to be like, I'm so confused. Like, get help now, right? It's not a big deal if you're brand new. And looking at, again, how these units work and why people like the metric system is that we have, right, our base unit, and then our metric system is based on multiples of 10. And so just kind of getting a feel of the units. So eventually we'll talk about moles, right? That's our special CHEM unit to signify a specific amount. And then, of course, length is going to be in meters with an M here, mass G for grams. Volume is in liters standard. Temperature, I'm going to put a little caveat, right? So usually we're in Celsius with our thermometers. But for thermodynamic relevance, we want to be in Kelvin. And so we'll talk about that later. So Kelvin. So I'm just putting thermodynamic relevance, and we'll get there in a little bit. So time, seconds, and then, right, we're not going to deal with information storage, but just to be clear, right, bytes. And so then I like this little cheat sheet here. I should have probably put it in my notes, but that's okay. And so we have, so this is multiples. And so again, this is like by our base unit. So giga, right, 1 times 10 to the 9th. Mega, 1 times 10 to the 6th. And that is also, again, on here. So we'll work on doing conversion factors. Centimeter, so now that's 1 times 10 to the negative 2, right, times our base unit. So this is all, again, by our base unit. And so let's do a little bit of writing conversion factors. And so I like using these conversion factors since it helps us with our dimensional analysis. So writing conversion factors. And so all we're saying, right, is we want to put our relationship in here. So let's just take giga for a second. And so then, right, if we have 1 gigameter, and again, looking at this is by our base unit. And I just picked meter since I like meters. And so that would be 1 times 10 to the 9th meters then. And then all we want to see with our conversion factors, and again, what we're going to be practicing with our recitation, is just writing it in two forms, right? And so all I mean by that is we can write our relationship one way, or we can say we have 1 times 10 to the 9th meters in 1 gigameter. Or again, right, for example, let's do micro now. So micro is 10 to the negative 6. So if we want to write, again, our relationships, and I would just put in parentheses, right, it's a relationship. So I don't want us to get confused by this, right? There's going to be plenty of conversion factors, relationships, energy relationships, right? I always like to say the only reason I survived physics was unit cancellation and dimensional analysis. And so we'll look at this. So 1 times 10 to the negative 6 meters is equal to 1 micrometer. Or we could write that as 1 micrometer is 1 times 10 to the negative 6 meters. What's also either confusing or helpful to think about is, so you can also do what I call like positive conversion factors. And so some people don't like negative numbers, right? But we can also rewrite this in another way. And so we can write it like so, or if you don't like negative exponents. So you can, of course, mathematically think about multiplying by 1. And so, right, I'm going to multiply 1 times 10 to the 6 times 1 times 10 to the 6, right, for both of these. So effectively 1. And I'm just trying to get out our other conversion relationship that 1 meter is 1 times 10 to the 6 micrometers, or again, writing that inverse. So 1 times 10 to the 6 micrometers is equal to 1 meter. So do we see how we have 4 different ways to kind of write that same relationship? And so it depends which way you're going, and again, whether you want to deal with positive or negative exponents, right? My only warning with the negative exponents is that usually somebody messes up the mental math somewhere. Obviously you can use a calculator, but with some of these, I encourage a little mental math. All right, so then that's what is going through here. And again, right, I'm encouraging us to use dimensional analysis because it will help us later, right? So I know you can do all sorts of methods, right? You can do proportions, blah, blah, blah. Some people just kind of do it without really knowing how they do it, I feel. But again, we want to be able to write out our work, right? Show our dimensional analysis so you better understand how to do it, and also so I can follow your work. And so again, all we did was write our relationship as in terms of conversion factors. And right, I'll give other examples, like we could say there's 12 inches and 1 foot, or 1 foot is 12 inches. So again, right, just writing relationships in different forms. And so let's do a little practice here. And so let's convert 600 megagrams to kilograms. So try that out for a few minutes. Just kind of see how it goes, see what you think.
Did you mean mega or milli?
Milligrams. Yeah, so 600 milligrams to kilograms. So how are we doing on this one? Does anybody want to describe kind of how they came up with the answer? Because there's probably like 2 methods at least. Any thoughts? So what do we pick as our conversion factors, right? That's always a good start. So we're trying to go from milligrams to kilograms. What could be a challenge for some people? How do we work this one? So how can we approach it? We have our conversion factors.
Convert milligrams to grams.
Excellent. So, right, that's what I was looking for. So this could be tricky, right? Not saying that this can't be done. So we're going to look at kind of how to come up with a relationship between the two. But yeah, if you're stuck, go back to your base unit, right? So again, this is our base unit. And I like to joke, right, this is also our safe space. So if you get confused, right, we have our conversion factors. So again, that's what we'll do on recitation is kind of work and just like write all these conversion factors. But if you want to just go ahead and do that, right, that's all we're doing is like, here are my answer choices of conversion factors, right? What do I pick? So, okay, we want to go milligrams to grams. So then what should I pick for my conversion factor, right? What's my relationship? And you can just start off by, before we even, think of how to plug it, what's the relationship between milligrams and grams?
1 times 10 to the negative third.
So I heard 1 times 10 to the negative third. So you mean 1 times 10 to the negative third grams is 1 milligram. I like using positive exponents, so 1,000 milligrams is 1 gram. Again, either one is appropriate. They'll come out. And so I'm going to use this one because I don't like dealing with negative numbers. And then, right, use your dimensional analysis tricks. Well, milligrams has to cancel, so I'm going to flip this, right? So now I'm going to write my relationship. Well, there's 1 gram in 1,000 milligrams. Okay. So that looks good, and I just crossed out my units, right? So they divided, so they canceled out. So now I'm left with grams. So now we want to go from grams to kilograms. So what's my relationship there? So right, you can always, again, look at this handout. So that's multiplier by the base, or this note. So what does it say for kilo?
For every kilo, there's 1,000 grams.
So 1,000 grams. So excellent. So 1 kilogram, 1,000 grams. And again, right, using dimensional analysis. And so, okay, I want the answer to be kilograms, right? So kilograms probably should be on top. And that's going to work out nicely, right? Because grams is going to cancel. So follow your units. And so now we could punch this into a calculator, or we could do a little bit of mental math, right? So doing your zeros. So then we get 6 times 10 to the negative 4 kilograms there. And so, right, just kind of sanity check yourself as well. So, okay, we're going from milligrams to kilograms. So I expect, right, we're going from a small unit to a big unit. So this should probably get tiny. So again, just kind of sanity check. You could also do what I call our one-step method. And so there's a couple of different ways to see that. But right, milligrams is 1 times 10 to the negative third. Kilograms is 1 times 10 to the third. So right, you could divide. And so right, doing a little mental math. So 1 times 10 to the third divided by this. So that gives us a 1 times 10 to the 6th relationship between them. So we get this right back out. So if you see this, great, right? Feel free to use it, and then you would just easily have your relationship. But, you know, again, the two-step method is completely appropriate. This is what I expect. I'm just kind of showing extra math tricks for people who see it. So I'll just kind of write it out just to prove, again, that we get our same answer here. All right, questions about that? Again, I know it was fast, so if you have questions, if you're being silent, definitely ask me for help. All right, so let's look at sig figs. And so this is really important. And so let's think about where it's from, right? So significant figures, they're not just because your chemistry teacher is insane and wants you to do all these crazy rules, right? It's reflected on the measured value, right, of our glassware. And so, you know, at some point, you know, probably not in this class, but right, at some point if you're doing like analytical chemistry or something, you know, you may really care about that, right? Like, how precise is my glassware? Is it even accurate enough to perform the experiments that I need to do? And so we want to practice that. So again, right, in lab, we're trying to reflect the accuracy of our glassware or our equipment. And so then, right, we want to be able to handle the calculations that accompany that. And so just some ground rules. And so conversion factors are treated as exact values. So all that means is, right, when you're trying to figure out how many sig figs, just ignore the conversion factor. So, right, we have 1 inch is 2.54 centimeters. So again, count it as infinite sig figs, not 1. That's all we're saying, right? So we have our relationships and our conversion factors. And so now let's kind of look through these rules, I'll call them. And so the first rule is pretty self-explanatory. So all non-zero values are significant. And so again, right, you're reading it from the balance or something, so you want to record every digit there that is non-zero, and they are again all significant. So this number, 536, has 3 sig figs, and usually I abbreviate like SF, or so if you see me like write SF or something on your homework, that's what I'm talking about, so significant figures. And then our next rule is also kind of, I think, simple enough, and I'll call this our captive zero. And all that means is if we have a zero that's between any non-zero values, it's significant, right? And that makes sense. So we have 6,703. And so our 0 is between our 7 and our 3. So that's going to be 4 sig figs. Again, that makes sense, right? You read it off a balance. You want to record all your digits. All right, so this is where it can get a little more tricky. So now we have our leading zeros and our trailing zeros. And I'm going to summarize this rule in that both of these show magnitude. And we'll look at this. So show magnitude, or you can also kind of phrase it how big or small, right? So a leading zero, again, it's showing how small, and so it's not significant. And so if you were to, again, right, let's say you're reading it off a balance, and it has 0.0043 grams. Well, we only have 2 sig figs, right? So again, these 2 zeros in front are merely showing how small. So they're trying to show magnitude. And we can rewrite it, right? So that's always a good hint too, is can we rewrite it? And so we can rewrite it to 4.3 times 10 to the negative third, right? Again, clearly showing that we have 2 sig figs. So if you can rewrite it in scientific notation kind of easily, that usually means that they're not significant. And so same thing with our trailing zeros. So again, they're going to show how big now. So zeros to the right are not significant. So again, let's say you have an elephant stand on a scale. So you have 7,000 here. And so you would only have 1 significant figure if you reported it like such. And so again, that could have implications about your balance or why it's important to record correctly, right? So again, you want to make sure whatever you're recording reflects the accuracy of the equipment. And so kind of what I mean by that, so let's say we have 7,000, right? But we want to show it is accurate to that 1 gram measure. Well, then we want to rewrite it as 7,000 with a period. So that's one way to show that that's significant. Or we could do 7.000 times 10 to the third, again, also showing that those are significant. So now showing significance. So, right, depending how you write it. And so if you needed to do something kind of trickier too, so let's say that this 7,000 was accurate to the hundredths pound, right? And so then, again, you could write it as 7.0 times 10 to the third, and now we're saying, right, accurate to hundreds. So again, this would go back to you have to look at your equipment and see what is the accuracy, right? What's the tolerance on that? And that, again, dictates how you report it. So hopefully you don't have something that's so inaccurate that you only have to report it to 7,000 with 1 sig fig, but that would be the case. And then again, this one here, so 32,040. Notice we have a captive 0, so that's significant. So 1, 2, 3, 4. But then our last 0, right, is now showing how big. So that is considered not significant. Questions on that so far? Does that kind of make sense? And then anything that's kind of, I call these extra or unnecessary zeros. Right, I'll say unnecessary. And I think I misspelled that. Right, and so kind of unnecessary zeros are extra, so they're showing basically how accurate now, right? So let's say we have this measurement 50.0. Well, the fact that they bothered to write that 0.0, right, that's telling us that it is accurate to the 10th place, right? And so again, that's probably reflective of a balance and the accuracy, so that would be pretty common for like a cheaper balance that it can go out to the 10th place. And then again for this one, so this would be a very nice balance to go out that accurately. So 3 sig figs. So again, this one is showing how big, and then these last 3 are significant. So again, right, showing accuracy. And so, right, our last digit too would be uncertain. So again, right, there's usually some sort of fluctuation in measurement in that last digit. Again, that's what serves as our limiting factor. All right, take a look at these for like a minute or two, and then we'll kind of flash through them, and you can throw up fingers at me, but go through them. So how many sig figs are in those examples? Just mentally write it down somewhere, and then we'll go over it.
Can two of the limiting rules be present at the same time?
Potentially, yeah. All right, let's run through them. So what do we think about 54,000? How many sig figs? Just show me some fingers there. So I see a bunch of twos. Excellent. So 2 sig figs. Good job. So again, those zeros are showing how big. And I might think about how to rewrite that, right? 5.4 times 10 to the 4th. And so that more clearly shows, right, those 2 sig figs. What about 304? So good, so 3 sig figs, so right, our captive 0. What about this one, number 3? Excellent, so right, I see a bunch of 3s, so don't get tricked by all these, right? They're showing how small, and then that last 0 is significant. So again, you might want to think about how to rewrite it. So 1, 2, 3, 4, 5, 6. So I'd probably write it as 2.10, and right now we can show that this is significant since it's accuracy, times 10 to the negative 6. And so now, right, that's a little more clear that all those were for how small. And then what about 4,500,000? How many sig figs? Good. So 2. So again, those were big. So 4.5 times 10 to the 6. And then what about this last one here? How many sig figs? So this one is tricky. So the correct answer is 2, but we can see why this is kind of a bad way to write that. So write the little period here, and I don't know if y'all can see that period very well. So it has a period, so it's trying to show you that yes, that 0 is significant. But again, right, not the clearest way to write it. You will see textbooks that do that, but it would be better to rewrite it as 1.0, right, times 10 to the 1. So you're clearly showing that that's significant. And you don't have, again, any ambiguities. Excellent. So y'all did pretty well on that one, though. Other questions, thoughts so far on sig figs? Again, ask me questions if you need it. All right, so now let's look at our temperature scales. And so I don't really make you like memorize this. You can, have your notes, so you can always write out our relationship. And so let's look at our different scales here. And so we're probably familiar with Fahrenheit, and then depending on your experience, you may or may not be familiar with Celsius. I like to tell people I know what a hot day is in Fahrenheit, and I know what temperature a bunch of solvents boil at, but it doesn't mean that I can tell you what a hot day is in Celsius. So there's that for you. And so, of course, Fahrenheit was set at 32 degrees, being water freezes, and then 212 is, of course, where water boils. And why that doesn't work nicely with our Celsius is, of course, there's a 180 degree difference between 32 and 212 versus 100 between obviously 100 and boiling. And then, so what is the Kelvin scale based off of? I kind of threw a small hint of thermodynamic relevance, but what is absolute zero? What is it based off of? Yeah.
Like the speed at which like atoms move
And then, so then what's absolute zero then?
when they stop moving.
Excellent. So yeah, absolute zero is the absence of all molecular motion.
Or the absence of any thermal energy.
Or thermal energy, so I'll add that. But again, right, molecular motion I like to emphasize because, right, even if you have a solid object, our electrons are still, right, moving around, they're still all vibrating, but then at absolute zero, again, all that would stop. And so we haven't achieved true absolute zero, but they have gotten pretty close at like 0.4 Kelvin or something crazy. And I didn't pull it up today, I wasn't thinking about it. But it's pretty crazy how they get to absolute zero now. So of course there's a lot of like thermal isolation that they're trying, but then now they like bombard it with lasers to try to like stop the molecular motion, so that they like hit it with a laser that stops the motion. It's really crazy how they get so low. Anyways, if you're interested, send me an email and I'll post some articles, otherwise I'll probably forget. There's a million things that I get excited about. But okay, so yeah, Kelvin is based off of absolute zero. So obviously, again, zero is the absence of molecular motion. And then it does track nice with Celsius because like Celsius, it was set that 100 degree difference is between water freezing and water boiling. And so the general formula, we can write that as our temperature Kelvin is equal to our temperature Celsius plus 273. And this is usually what I use. And then if you ever see, this would probably be in your homework or other like cases, this is the more exact factor, so like 273.15. But that being said, so right, our thermometers are only so accurate, so usually we just measure to like the nearest whole degree, again, for our purposes. And so for the most part, I ignore this 0.15. The only time where you might see it come up is if it asks for exact. And I believe that's in the homework. But you'll see what I mean. And otherwise, I'm not going to be picky about it on an exam. Like, I'm not going to test you, oh, convert exactly, and then I'm going to be like, oh, you didn't do the 0.15. Like, not that concerned, right? I'm just kind of putting it there so you know it's there. But again, for our purposes, 273 will work fine. And then, okay, blah, 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 Fahrenheit. So like I said, I'm probably never going to test you over this explicitly without, providing the formula. That's not the nature of this class, is to make you memorize a bunch of unnecessary formulas. Oh, and so that's what this periodic table is for. So eventually I'll talk about the exams and stuff. I haven't quite figured out how I want to do them. I won't get into that right now. But basically, this is your cheat sheet for chemistry, right? I printed it on hardstock, so hopefully it survives. If you need more, just ask me. I'm happy to give you more. But that being said, right, anytime you come up with a formula that you want to write down or some concept, right, use this as your cheat sheet. And eventually, right, we'll mark up the periodic table for other concepts, but, right, this is your lifeline for chemistry. And, yeah, not to get, like, too much into the exams, because, like I said, I don't know how I'm going to do it, but I don't like to do a bunch of just rote memorization, right? Because, again, as a chemist, you're always going to have your periodic table. You can look up formulas all day. It's still just, can you apply them, which, you know, is the hard part. And so then, that being said, right, there's our Kelvin formula. So you may want to write it down. Again, I don't think we do too much thermodynamics, so we'll touch on enthalpy at the very end of this quarter, and that's when you might need it, but otherwise just kind of keep that in your back pocket. And so let's look at density then. And so density, and this is, again, just trying to put us in the correct mind frame of dimensional analysis. And then looking at, let's actually define a term here and why density is useful. So we'll come back to this. But what's an intensive property and what's an extensive property? And where does density fit into this? So anybody?
Density is an intensive property.
So density is intensive, and so what is intensive then? Do you have a definition?
Is it like intrinsic?
Yes, or like inherent, intrinsic, yeah. Maybe let's still define it. Intrinsic, so what does that mean? I can't spell, obviously. And why would density be relevant? What can we use density to do with these words? We're all there, but I want to just clearly define it.
Define the mass volume proportion.
Yeah, but then what do we do with that mass volume proportion? What could we do with it? Yeah.
Make predictions?
What kind of predictions?
Buoyancy.
Or experiments?
Now I think we're thinking too hard. Like, just if it's intensive and we have a density of some object,
Then we could figure out its mass given a volume or its volume given a mass.
yeah, but more than that, right? We can. What I'm trying to get at is the identity, right? So every substance has a specific density. So we still haven't defined intensive. But what would that mean if we have an intensive property? Maybe what are other examples of intensive characteristics?
Atomic number?
What did you say, sir?
Atomic number?
So atomic number. What else?
Would melting point be one?
Yes. So melting point, I'll put boiling point too. So that's all kind of getting at the same idea. We haven't quite said it, but so intensive property, I'll just define it. So it does not depend on the amount of substance. So all of y'all, you kept telling me the density volume rate or mass volume ratio, which was perfect, right? So you always have a mass volume ratio, but that means you can always calculate the density, which goes back to the identity, right? So these are good ways to characterize and perhaps identify different substances with their intensive properties. And so, right, you guys did a good job at naming some. So, right, atomic number. So that doesn't depend on the amount, right? Same thing with melting point, boiling point. Those are standard for whatever molecule or element we're looking at. And so then, let's add a few more. So what would other intensive properties be? What else could we think of?
Would conductivity be one?
Yeah, that would be a good one. So conductivity. What else?
Reactivity.
reactivity. So, right, doesn't matter how much sodium we have, it's always going to explode with water.
Oh, how radioactive it is, the decay rate.
Radioactive, decay rate. I like that. I'll just throw in some other ones unless, I don't know if anybody wants to chime in. So I have hardness as well, state of matter. And I'm sure there's others, but those are kind of the main ones. Again, right, just thinking of how you can identify elements. Reactivity is a good one, right? You'll kind of do that at some point, kind of investigating reactivities. So again, you can figure out what substance is which. And so that being said, what's an extensive property then?
Size.
So size, what else?
Weight.
Mass, weight.
Shape.
And so how would we define extensive then? So if intensive, right, does not depend on the amount.
It does depend on the amount.
Exactly. So, right, so extensive does depend on the amount. So again, right, size is usually a good one. Length, width, volume. Right, so obviously you're going to have a specific amount. All right, so let's look at density then and kind of practice this. So like y'all said, it's just a ratio of mass to volume. Again, great way to kind of at least quickly try to characterize substances. And so a couple of things, right? So you can, of course, use your dimensional analysis. I also like showing people this little triangle trick if you guys have never seen it. And so you cover whatever variable you're solving for. So let's say you're solving for mass, right? You cover it up and then it tells you what to do. So you should multiply density and volume. But you could also see by dimensional analysis that that would be true. So, right, density is grams per milliliter, multiply it by volume, and so you get grams back out. So again, right, use your dimensional analysis. And so let's try this problem here. Well, let's try this one first. So we have 73.2 milliliters of a liquid, and it has a mass of 61.5 grams. So what's the density in grams per milliliter? And I'm also going to remind you that a centimeter cubed is a milliliter. It will come up eventually. So then this one, again, fairly straightforward. So density is mass over volume. We're given mass, we're given volume. And so for density, right, you could have different units too of like mass and volume. So just keep that in mind, right? It's just a ratio. So just watch your units. But again, that's kind of in our standard units here. So 61.5 grams divided by 73.2. And so what do we get for our density? You said 0.84. And then don't forget to tack on a 0 to that, right, for sig figs. So we'll have to go through our math with sig figs later. But kind of basically, so when we do multiplication and division, we want to report to our least number of sig figs. So we had 3 in our milliliter, 3 in our gram, so we should have 3 in our answer. So we don't want to lose accuracy. So like I said, we'll keep practicing with this. And then let's try this one before we go. So again, use your dimensional analysis, right? So you're trying to find volume now. You could also cover this, right? So trying to find volume, it's telling you I should do mass divided by density. So go ahead and try that one.
Usually my room is next. Now they changed my room on me.
All right, so what do we get for this one? Do we get A? What about B? C? D? So everybody like D? And so yes, and so I just kind of wrote out the dimensional analysis, right? Grams cancels. Again, triangle trick help, but then we can see, right, we're left with centimeters cubed, which is our milliliter. So yes, D there. So we still have a bit of chapter 1 to finish. So we'll finish up a little bit of chapter 1. So just kind of, again, looking at dimensional analysis with our energy units, and then going over kind of our mathematical operations. And then hopefully we'll get into chapter 2 as well. If not, that'll bleed over into next week. All right, so don't forget lab today. So if you are signed up for the Tuesday lab, it's just down the hall, 312. So get snacks, get food. You know, there's a cafe downstairs, vending machine on the 3rd floor. So get substance, and then I will see you in lab. Thank you, thank you. Make sure to get the handouts. And I'm going to end our stream here.
Yeah.